I've been talking today about our recent work, which is focusing on enhancing simulation-based optimization through mixed integer programming. And I'll be specifically talking about our case study in autonomous ride-sharing. Urban mobility logistics, as we know, there are three main classes of problems that we frequently solve in supply chain and also in transportation, namely facility relocation problems, but also vehicle routing and scheduling and inventory management. So when we bring all of these fields together, these classes of problems, we have autonomous ride sharing. So what happens in autonomous ride sharing, as for many other problems, both in supply chain and logistics, is that we have a lot of uncertainties in reality. So we may have traffic congestion, which delays the operations. We may not know from a start the demand, where the demand is located. The vehicles may break down during the operations or even before the operations. And in the case of autonomous ride sharing, we are using electric vehicles. So these vehicles need to recharge, and recharging stations may not be always available. So all of these uncertainties affect autonomous ride sharing operations. And there have been many techniques that have been developed to handle uncertainty, not only in the context of autonomous ride sharing, of course. So we have, of course, stochastic optimization, in which we typically have a few sources of uncertainty. We can model uncertainty through complex objective functions, and uncertainty is typically given to stochastic optimization models as an input parameter, so essentially distributions of the uncertainty. And then we have the field of simulation-based optimization. What is the difference? The difference is that in simulation-based optimization, we typically consider multiple sources of uncertainty. We have intricate objective functions, not necessarily complex, of course, and we may have nonlinear interactions between the sources of uncertainty. So these, let's say, all of this uncertainty has been typically modeled in our field through three main classes or three main fields, which is the machine learning field, the simulation field, and the optimization field. These three fields sometimes are worked in parallel, sometimes together. And when we bring them all together, we have the field of data-driven optimization. And of course, we can go in all directions. So we can try to help, say, optimization models through machine learning, or the other way around, of course, which is very common. So machine learning through optimization, but also machine learning for simulation and so on. So we have all possible directions of interactions between these fields. And here, what we're going to focus on is how can we use optimization to help, in this case, simulation-based optimization. So optimization based on simulation. And the focus here will be on discrete problems with very large parameter spaces. So discrete simulation-based optimization, essentially we have, of course, a simplified optimization model, which is a simplified version of our reality, also called a meta model. And this is typically, for example, in the case of discrete problems, it's a mixed integer linear program. And this simplified optimization model can be both used to produce feasible solutions, of course, but also to focus simulation of effort in subspaces of the feasible region, which we deem more interesting. And then, of course, as I was mentioning, we have the simulator part, in which we try to reproduce the non-linearities, so the reality, for example, through an event-based simulator. And so the job of the simulator is both to evaluate the objective function of the solutions provided by the MILP, but it also could be to produce new solutions which were not produced by the MILP. So you can already see that we have these two blocks, and the connections between the two are quite intricate, and they go both ways. So in some cases, we would like to inform the simulator through an optimization model, but we would also want to give a feedback loop to the MLP through the simulations that we run. The issue is that running simulations is very expensive typically, because we need tens of thousands of simulations to carefully estimate the objective function of the solutions given by the MLP. And so our goal here is to be able to focus simulation effort on subsets of solutions which are deemed most promising. DSO algorithms, we have the class of random search methods, and we have essentially two main possibilities. One are methods based on partitioning the search space, such as nested partitions or empirical stochastic branch and bound. And then we have methods based on exploring neighborhoods around solutions. So these are, for example, COMPAS or AHA. If we want to make a parallel with operations research, this would mean that the first class could be seen as similar to branching on variables in branch and bound. We try to split the search space by fixing decision variables. And the second class of methods is more like local search meta-heuristics, in which we try to explore the search space relative to a specific solution. So I'll give you an example of nested partitions, I think is the best way to go. So suppose that we have the entire feasible region. This is theta here, and all the points that you see here is a routing solution. It's an MILP solution. Now, what nested partitions does is that it starts by providing a partition, so a split of these two solutions based, for example, on a decision variable. Say I want to fix certain decision variable to either 1 or 0. Okay, so we have one set of problems, the blue problems, and then we have all other problems on the other side. We then simulate some of the solutions. Suppose you have a sampling mechanism that samples some of the solutions in the two clusters, sigma 1 and sigma 2. And then what we do, so we select some of these, it's the sigma 1k. And what we do is that we compute what is called the promising index function, which maps the solutions to a scalar. So it could be, for example, that after simulating the sample solutions, I would like to select the region that provides me the best of simulated objective function value. This is, of course, a choice. It's a function that is up to the design. And then we continue. So suppose that the blue region has been deemed as the most promising according to the promising index function that we have chosen. So then we resplit that specific region. So we provide another cut, essentially. It's a cutting plane. And we have two regions now, the blue, the red, and then we have a third region, which is the black, which is also called the surrounding region, essentially the region that does not contain the decision variables of the most promising region. And again, we resimulate some of the solutions, we sample some of them, we may add additional simulations to solutions that we already simulated, we may sample new solutions. And again, we suppose that we find that the red region is the most promising. Then what happens is that we merge the areas that are not deemed promising into, again, what is called the surrounding region. And here, again, the goal is to be able to focus on a subspace of the entire feasible region so that we can focus as much as possible simulation effort on solutions that are being more interesting, such as in the red region. And here again, we can continue splitting. Again, on another decision variable, we set it either to 0 or 1 because we are talking about a binary problem. And at some point, it may happen that because we add simulations, and simulations add stochasticity, we cannot add all of a sudden a lot of simulations, we may realize that we've made the wrong decision earlier on. So we may need to backtrack what we've done before. And so we may find out that actually the region that was the black region, so the surrounding region, the region that we thought it was not interesting, is in fact now the most interesting region. So we move to that region, and again, we continue partitioning, we start partitioning again. So as you see, it's an iterative process, quite simple in its ingredients. We have a partitioning rule. So we need to decide, for example, on which decision variables we would like to split the feasible region. We have a sampling rule. We need to decide how we sample solutions in each region. We have a promising index function, which essentially is there to give us an evaluation of which region is most interesting to simulate. And we need to have a backtracking rule to essentially go back on decisions that we've taken, which may not necessarily be great at a certain iteration. So the goal here of this project is, can we derive smart partitioning rules using information provided by an MILP? So we focus on the partitioning rule, but of course, all of these ingredients are equally interesting. So the benchmark in the literature, I'm quite lucky. There is not so many cases of so many partitioning rules for discrete problems. We have generic partitioning rules. So this is problem independent. Suppose most of the problems, actually what they do is that they relax the mixed integer program, which is typically NP hard, so it's difficult to solve. And they rank the decision variables based on their deviation, say from 0.5. And so then they start partitioning on the decision variables that which are closer, say, to 1 or closer to 0. This is very generic, of course. But then we also have problem-specific partitioning rules. So here, without going into much detail, what we are seeing at TSP, in which we have 5 cities, and what they do in this work is that they rank the cities closest to each one of the list, essentially the distance between each city, A, B, C, D, and E. And they start partitioning on the 2 cities which are the closest to each vertex and each city that is the further away. So as you see, this of course gives a tree. Some of these, let's say, groups of roots are infeasible because because of the problem because of the TSP. So you come up with a number of options that you have, and this is a quite simple rule that specifically depends on this graph, so on the problem. So as I was mentioning at the beginning of the presentation, we are focusing here on ride-sharing applications. So in ride-sharing, essentially ride-sharing can be solved through a dial ride problem, which is a generalization of the DRP or the TSP. So as we know, since the TSP is NP hard, then the DARP is also NP hard. And this has been modeled in many different ways, going back to one of the original papers in 2003. And what we have is, we simply have a graph composed of the vertices and arcs. The vertices represent the vehicle depots, so where the vehicles are parked before service, the pickup locations of the customers and the drop-off locations of the customers. We typically have a set of vehicles that need to provide service to these vertices, so these customers, and we have arcs connecting the vertices, which are the vehicle movements. So it gives the route of the vehicle, so the sequential visits of the customers. And typically we need to track these vehicles. So we need to say the decision variable is X, I, J, K. So it has either it has 3 dimensions, in which we try to say which vehicle moved to which couple of locations, right? So this way we can track vehicles. There have been some extensions in which researchers have demonstrated that this problem can even be formulated through 2D art. So we don't need to explicitly, let's say, track the vehicle in the decision variable. Anyway, obviously the goal is to find minimal cost routes so that we can serve all of the requests. And we need to serve all of these requests with some constraints. So of course, vehicles have a maximal capacity, but also we need to provide service to the pickup and the drop-offs within some time windows. We cannot pick them up or drop them off whenever we like. And we should try not to delay passengers too long. So in this problem, again, passengers can share a ride. And so when they share a ride, they don't have a taxi service, they have like a Uber pool service. And in that case, we should make sure that we don't bring them around the city all day long, right? So we have maximum ride time constraints. So this is the classical DARP. Now, when we are speaking about autonomous ride-sharing operations, what we do is that we build on the classical DARP, which is NP hard, and we add a number of features which of course complexify the problem. So autonomous vehicles are typically electric, so we need to, of course, manage the battery inventory. We need to plan for intermediate visits to charging stations. We need to choose how long we should charge. And with respect to the autonomous nature of the vehicles, well, what happens is that these vehicles can give 24/7 service. So they need to continuously relocate within the city in a smart way so that they can provide service to the next requests that are coming in the future. Of course, there are no maximal route duration. In classic DARP, we also have a set of constraints that essentially limit the length of a route because we have physical drivers, we have human drivers, and these drivers have shifts. In the case of autonomous vehicles, there are no shifts because there are no drivers. So this set of constraints are relaxed in the case of an autonomous ride-sharing problem, which actually makes the problem harder because all of a sudden we have many more solutions. Anyway, so in autonomous ride-sharing, we have this very complex problem, and so there are a number of drawbacks here. Of course, it's a very hard combinatorial optimization problem. To solve it, to be able to solve even very small instances, we need to implement hard, very difficult solution methodologies, such as branch and cut or meta-heuristics. And so when we solve this problem, we have a very slow convergence as a result. And sometimes it's very difficult to even find just a feasible solution, let alone convergence. So while I was reviewing the literature, I came up, I noticed a very recent paper in which the authors propose a new way to describe the graph for ride-sharing operations, so for a dial a ride. And in this work, what they do is that they rethink completely the graph. So now all of a sudden the vertices are not pick up and drop off locations, so not location of people, but they are states of the vehicles. What I mean by states, we have an example here. So suppose that we have vehicles with a capacity of 3. So vehicles can only contain a maximum 3 passengers. And so we have tuples with 3 entries. An entry that is 0 means that there is no one on board. So when we start at the depot, the vehicles are supposed to be empty. So we have empty vehicles 0, 0, 0. A vehicle with capacity 3 and no one on board. Then here in this case, we have a simple case with just 3 requests. And the plus sign indicates pickup locations and the minus sign indicates drop-off locations. So what we have here is, for example, we have tuples with 1 plus 0, 0. What it means is that the vehicle, the state of the vehicle is just picking up a customer and has no one else on board. Equivalently, if we have 1 minus 0, 0, it means that the vehicle is just providing a drop-off service, but no one else is on board. When we have tuples which contain more digits, is the first digit indicates the current action of the vehicle, while the other digits essentially indicate the other passengers on board. So 1 plus 2, 0, for example, indicates the vehicle is picking up customer 1, but also customer 2 is on board. So essentially, customer 2 was picked up before, right? So this is a nice way to see the graph, because each vertex in the graph does not only give information about the location of a customer, but it gives information about the action of the vehicle and partially some history of what happened before. So the arcs here, what they do is that they really just connect vehicle states. So it's just one-dimensional, right? We are moving from state A to state B. So just xi, one dimension. So yes, to recap, the state set are tuples in the size of the vehicle's capacity. Because these tuples are in the size of vehicle capacity, this means that the graph itself already takes care of capacity constraints and also precedence constraints, right? You cannot drop off someone before you pick up someone. So essentially, you remove all of the states which are deemed infeasible. And you can also, so when mentioning each state also brings more information about what the vehicle is doing or has been doing in the past. And as we already take care of capacity and precedence constraints, we actually also already take care of time window, partially time window and write time constraints. Why is that? Because since we have the customers within the same vehicle, such as 1 plus 0, we can easily check whether it is possible to.
Can I ask you just a
quick
question?
Sure.
Here you have like 3 numbers, so I understand the first 2, but the last one is always 0.
Yes, in this case, in this specific example, yes, I haven't reported it here. So normally associated with each request, you also have a load. It's like in pickup and delivery. So in this specific example, 3 plus brings a load that is greater than 1. And so in this case, you don't have to go with the 3 digits because the vehicle cannot afford to transport more than 3 people. But it's a specific example that yeah. But yeah, in general, you can fill all of the locations if the load is coherent with the vehicle capacity. And so yes, essentially you can get rid of many of these states just by checking whether 2 customers can be served together in terms of their time windows. So if I pick up Lea, say, and then I go and I pick up J, well, maybe they gave some times, right? They said, I want to be at Andrea Eisenstadt at 11 a.m. Lea said this, and J said, well, no, actually, I want to arrive later because I don't care about this presentation. I want to arrive at 3 p.m. So, well, then obviously a vehicle cannot just pick up Lea and then pick up J because their time windows are not compatible. So we can get rid of a lot of states just by using the constraints of the problem. And this is why this model is interesting for hardly constrained problems, which can be, again, electric autonomous ride sharing in general, but also pickup and delivery and other problems that contain a lot of constraints. This is not typically a formulation that is very interesting if you don't have a lot of constraints. And here I show a simple example. On the left-hand side, we see a number of instances. These are taken from the DLR literature. And what I'm doing here is that the column DARP, so the first column, indicates the time that it takes to solve this very small instances problem. 2 and 16, for example, indicate 2 vehicles, 16 customers, 2, 20, 2 vehicles, 20 customers. So you see that these are small instances. So if we solve a classic DARP, the first one that I showed to you, the graph is like it's people, pickup and drop-offs, and we have 2D or 3D arcs. We can take already a very long time just to solve super small instances. We see an instance with 3 vehicles and 24 customers without any fancy solution methodology. Takes already 818 seconds to solve. And now we see EB DARP is the event-based DARP, so this new model. And we see that as we reduce the state space by different constraints, so capacity constraints, and then capacity and windows, and then capacity and windows and write times, the model becomes more and more interesting. So in the last column, we have reduced the state space by all of the constraints of the problem, and we see that the same problem, 324, that took 818 seconds with the classic DARP, without any solution methodology, of course, now it takes 0.24 seconds with this new model without any solution methodology. So it's an interesting formulation. And so I kind of lied to you. I told you that I was going to talk about autonomous ride sharing, but here we are starting from classic ride sharing. I just took this formulation and said, okay, this is very interesting because I will be solving MLPs many, many times during the simulation-based optimization approach. And so I'm looking for something that is fast to solve. So if we go in the details of the formulation, what we have is a set of transport requests R. We have pickup and drop-off locations, I plus, I minus. We have sets of pickups, sets of drop-offs, a set of vehicles. V is the entire vehicle state, the tuples that I showed you before, which can also be split in the tuples that correspond to pickup locations and tuples that correspond to drop-off locations. We have the complete arc sets, the connections between these tuples, and arcs that only enter and only exit such states. And in terms of the parameters, of course, we have a number of transportation requests. As I was mentioning, we have time windows. So we have earlier start time and later start time at every tuple in the space. We have maximal write times. We have our costs. And as for the decision variables, what we're trying to find is XA, so the binary variables that indicate if a certain arc is used, which means whether a certain state is used, of course, and BV, which is the timing. So it's a continuous variable indicating the start of service at each tuple that is visited. So what we have is essentially, it's very similar to a classic DARP model. We want to minimize, again, our objective function. We want to minimize, say, the cost of transportation here. And we need to enforce flow conservation constraints. Once we enter nodes, we need to exit nodes. We are enforcing that all requests are served. So once I have a set of requests, I need to be able to give service to everyone. I have a maximal fleet size, so I can use only at most the vehicles that I have. But then also I have constraints with respect to timing. So I need to be able to track the times at which vehicles started giving service, and also to make sure that these services lie within the time windows of each of the tuples, while providing service in a reasonable way to the customers. So making sure that right time constraints are not exceeded. And so this is essentially the model. And now the question is, this is the MLP that I will be using to help the simulation-based optimization. But so what is the discrete simulation-based optimization problem, right? I was telling you that this is a harder problem, which we have a lot of uncertainties. So what would be the model in this case? Well, in this case, what we have is that the objective function is no longer this very nice linear function, but it's an expectation of some complicated function in which we take as an input the routing decisions and the timing decision, and we have a number of uncertain events, nonlinear complex Z, that appear. So what I'm trying to do is to minimize the expected value of essentially the cost of the route. And then we have what are the uncertain events that can appear. So of course, requests can opt out. Suppose that someone decides that they don't want service anymore. Well, they can obviously opt out. But also it can happen that because we have delays on the arcs, so because the arc length can increase or decrease, then vehicles can be late. And so customers don't want to be served anymore if there is too much delay. Vehicles can break down during service. So we can have less than K vehicles. We may have K-1, K-2, or even more. And as I was mentioning, vehicles can arrive early or late. So we may have delays on the arcs. So the arc length can change. And so time windows constraints are no longer there. And requests as a consequence can be transported for longer or a smaller amount of time. And all of these, let's say, events actually come into play in the objective function. So these are constraints which are relaxed, but also they affect the objective function, which is an estimation in this case. So we need a simulator to be able to represent all these events. And for now, I have implemented a very simple event-based simulator. Here, as you see, we give as an input to the simulator the vehicle routes and schedules, of course. And what happens is that we start producing, we have essentially 5 possible events. Let's start with the event 2. So at the beginning, of course, we have vehicle departures. Vehicles are, should depart. And as they depart from a node, they arrive at a node, which is event 5. And then as they arrive, they need to either give pickup or drop off service, right? So event 3 or 4. But what happens is that we may have delays on the arcs. So the route length may increase or maybe decrease. And so these arc delays will affect the arrival of vehicles at nodes, which of course will affect the time at which I pick up, drop off, and vehicles depart. So it's a simple, in the structure, it's a simple simulator. Of course, the nice feature of event-based simulation is that it's modular, right? So you can always add additional events that represent, for example, customer opt-outs or other stochastic events which are not displayed here. So partitioning ideas, as I was mentioning, we are taking inspiration from nested partitions, the example that I gave before. And the question is, okay, so now that we have this simulator, now that we have this event-based mixed integer program, what do we do with it? How do we partition the space now that we can produce solutions with the MILP, but we don't really know which solutions are good or not according to the simulator? So there are, as I was mentioning before, there are generic partitioning ideas, not necessarily linked to Ridesharing, so not necessarily linked to dial ride. And so one could extract information from the branch and bound tree as I solve the mixed integer program. And for example, one could retrieve on which variables I branch the most. I can retrieve, for example, which variables push the bounds the most while I solve the branch and bound tree. I can also retrieve, for example, which variables produce the shortest branches when I look at the depth first searches in branch and bound. So this is using the event-based MILP to essentially retrieve variables that may be more or less hard for the problem to set. In the first case, for example, if I branch very frequently on a variable in a branch and bound tree, maybe this suggests that this variable is particularly complex to set. So maybe I want to set it to 0 and 1 and analyze how this choice impacts the objective function of the simulator. So this is generic partitioning, but we can also have problem-specific partitioning ideas, so that which uses the problem structure of dial ride specifically. So one could look, for example, at the assignment of requests to vehicles. So in this case, if we have two solutions, for say that in which the same customers are assigned to the same vehicles, but maybe the sequence is not the same. So in one solution, I pick up Lea first and then I pick G second, but maybe in another solution, I pick up G first and then I pick up Lea second. So in this case, we would have an handling distance of 0, right, between these solutions. So can I count, for example, the number of solutions which have a handling distance of 0? And if so, does it mean that it's very easy to assign customers to vehicles, but maybe the sequence is not so easy? Or we can also look just at specific segments of a route. Maybe two routes are not all the same, but maybe part of this route is the same. So maybe some customers are very easy to schedule, but some of them are not so easy. So essentially, we would be looking at sequences of visited nodes, such as like in DNA, right? So sequences of. So these are all ideas that we have in mind. Now, just to give you some examples of our preliminary results, I have implemented all that I talked to you about. So the MILP, the simulator, using my essentially commercial laptop. And I've implemented using Julia and the JAMP library. And I'm using now Gurobi as a solver. The Ridesharing instances are essentially the instances that I showed you before when I presented you the event-based MILP. And they're taken from the literature. And so for now, we are focusing on small-scale instances. We still want to know what is going on, right? The goal will be to expand to large-scale instances. So we have 2 to 4 vehicles and 16 to 24 requests, very, very small instances. With respect to the discrete simulation-based optimization settings, I'm now setting just 100 iterations, very small search. And what I do is that through the MILP, I'm producing solutions to be evaluated with the simulator. So at every iteration, I may add additional 100 solutions per partition. When I sample a solution, I add 100 simulations per solution. And with respect to the simulator, our delays are drawn from a truncated normal distribution with mean 0, and the standard deviation is a percentage of the direct travel time. What I mean is, actually, maybe it's better to give an example. Suppose that a vehicle is traveling from node A to node B. So the travel time that is used in the MILP is TA to B. But now we have a delay on this arc. So this delay, for example, may appear after the vehicle has departed from A. And this delay is given by this truncated normal distribution, which is a percent in which the standard deviation is a percentage of TAB. And so we see that on the right side, the positive delay, so the arc can become longer as much as we want, say 3 times sigma, just to not make it go to infinity. But on the other side, the arc TAB can become shorter, but not freely, right? So the vehicle cannot go back in time. So to the very best, what the vehicle could do is essentially fly from A to B, so that TAB becomes 0. So that's how the simulator works. And here we have an example. Suppose that we have this route. Nodes with P indicates pickups. Nodes with D indicates drop-offs of the customer that is indicated by the ID, for example, customer 10, customer 5, and so on. It's an example of a route. Now, what happens in the simulator? So the MLP has given me this route, and also the MLP has given me an optimal schedule according to the MLP. Now, when I put this route in the simulator, what happens is that I may have a delay after the vehicle has departed from the depot. So this affects the arrival time at P10. But what can happen is that actually in the original schedule given by the MLP, vehicles were waiting before providing service to P10. So this delay that happened between D and P10 has actually no effect on the schedule because it's absorbed by the waiting time of the vehicle, so the idle time. I may then have, for example, negative delays, as we've seen. It's drawn by this truncated normal distribution. So I could arrive earlier at nodes, but again, this could also have no effect because there is waiting. And then I could have again positive delays and so on. At some point, suppose that positive delays happen at all subsequent nodes. What happens is that when I arrive to D15, all of a sudden, not only I've arrived later because of the summing up of positive delays on arcs, but moreover, I've arrived, sorry, this should be out of time window. I've arrived outside of the time window of D15. So this means that the customer that was expecting a vehicle by a certain time didn't see the vehicle arriving. So for example, 15 could drop out of the system. So this is an example how the simulator works. So what I started doing is implementing the simple benchmark strategy from the literature. What they do is that they take the optimal values from the relaxed problem, which is the MIP. They relax the MIP, they solve an LP essentially, and they retrieve the relaxed decision variables. And they order them by taking their absolute deviation from 1/2. So this means that, for example, X1 is deemed to have the highest deviation from 1/2, and then X2 and so on until Xn, all of the decision variable. And then they partition the region taking, for example, X1. So they either set X1 to 1 region, or X1 to 0. And so what is the rationale here? The rationale of the literature is that, well, a variable that, for example, has a value 0.95 in a relaxed solution, maybe in an integer solution, this variable is more likely to be 1. So it is a heuristic, if you want. It's a very simple heuristic, which has been developed in the literature. Now what I did is that if we go back to the MILP, so what the partitioning that I'm proposing, which is based on a MIP, then what I can do is I can retrieve all of the variables of each decision variable. We have 344 decision variables on the x-axis. I can retrieve their values between 0 and 1. Most of the nodes have value either 0 or 1. And this is just a pictorial image of what the solutions look like. We have thousands of solutions in a branch and bound tree. And we see, what can we see? We can see that in many of these solutions, some decision variables are essentially always 0, right? And some of the decision variables are essentially always 1. The yellow part indicates 1. So by just inspecting this, I was thinking, okay, what can I do with this information, right? It's time to be creative. And the first creative idea, not so creative to be honest, is let's take the generic partitioning that it's proposed in the literature. So deviations from 1/2, but instead of using the values from the LP, let's use the average values from the MLP. So essentially, if I take one column here, one of the X decision variables, well, I take the average value of this decision variable. It can be most likely 0, most likely towards 1. And so I start essentially partitioning based on this average values of the X on all of the nodes of the branch and bound tree. And then, as in the literature, I partition the region by setting, for example, X1, which is the variable with the highest deviation from 1/2 to 1 or to 0. So really the difference between this generic partitioning or the partitioning that was proposed in the literature for now, this is preliminary tests, is just, do we use information from NLP, which solves very fast, or do we use information from a MILP, so all nodes in the branch and bound tree? Is there any added value in using the MLP, even so simply? So another thing, note that in general, so now I'm focusing on a very small scale instance with just 2 vehicles and 16 customers. We have 63 nodes, 344 arcs. And so if we solve an LP, of course, solving an LP as per the benchmark partitioning is almost instantaneous, right? It's super fast. So it's 5 milliseconds. Solving the MLP, okay, sure, it takes longer. I'm using this new formulation, which is nice. It's still faster than the classical formulation, but it's still 15 to 20 milliseconds. But each simulation takes 20 milliseconds. It's not a lot if you consider one simulation, but you need to remember that we are trying to estimate a distribution for each solution, right? A distribution of the objective function, of the simulated objective function. So we need a lot of simulations. So suppose that I'm, as I was mentioning, I'm at every node adding 100 simulations for every solution that I sample. Then what we have is the time of the simulations times 100 simulations. Okay, the simulations, I can do them in parallel. Suppose I have a quad-core computer. So the time for the simulation is split between the 4 cores. Then I'm simulating 100 solutions, right, for every partition. And I have 2 partitions every time. So every time I create 2 additional partitions. So we have just about 100 seconds just for the simulation. So this is to say that essentially the solve time for the partitioning, it's really relevant with respect to the simulation time. So again, this shows that it is important to be able to focus simulation attention on solutions that we think are more interesting or promising, because then we wouldn't spend time simulating solutions that are bad anyway. So preliminary results. So I've run the benchmark partitioning and this very simple first approach. And the first thing that it's interesting to note is that you remember that you have this backtracking rule. So every time you took a decision about partitioning that was not really good, you need to be able to go back to a region that is larger to repartition again. So one of the elements that could indicate whether a partitioning is better than another is how many times in this iterative process I had to backtrack on decisions that I took before. And so if we use an LP, we see that we backtrack 11% of the times, whereas if we use information from a MILP, we only backtrack 1% of the times. So this is already, this is good, because again, what we would like to do is to focus attention on the partitions, not on the surrounding area. So if we only backtrack 1% of the time, we are focusing attention on the right partitions. Here, what we see on the left side, we have the partition time. So, sorry, the scales of the y-axis between the two figures are not the same. Both axes are in seconds. And in the first figure, what we see is that essentially the benchmark partition solves instantaneously, right? It's an LP, super fast. The simple partition takes a bit longer, as we've seen. But on the right-hand side, what we see is the simulation time. Now, why does it take so long to simulate solutions when we use partitioning mechanism from an LP? Well, it takes so long because remember that I was mentioning that every time that I partition, I resolve the MLP for two reasons. First, for partitioning, of course. But the second thing is that I solve the MLP to find new feasible solutions. So when I partition and I don't partition the solutions very smartly, what happens is that all of a sudden, the MLP is giving me more and more and more solutions to test with the simulator. And so because I sample the solutions from each partition, because I simulate the solutions from each partition in this very simple example, what happens is that the simulation time for using an LP goes really up. Yes, so here, for example, using the LP, we have thousands of solutions, whereas using the MLP, we stay in the best, say, 200 solutions. That's why it's so low. So, okay, of course, one wants to see what happens for the objective function, right? And so what we see here on the left-hand side, we have the objective value for the benchmark partition. Sorry, yes, that is the benchmark partition between the MLP, which is the dashed line, and the simulated objective function, which is the solid line. So on the left-hand side, we have the benchmark partition. On the right-hand side, we have this new simple partition based on the MLP. We cannot really see much difference, right? I mean, it seems like at the end of the day, the solution that we get as the optimal solution, or even across iterations, they seem to be the same. And here, more specifically, also, I was focusing on simulation effort on the partitions. So I was expecting to see some better results using the MLP. Not really, of course. The issue is what? The issue is that I'm testing an instance that is very small. So in this case, this means that the difference in the objective function, even for the MLP across solutions, is very small. I mean, if you have a small instance, you don't have so many ways to route requests. So at the end of the day, if you take one route or another, it's not a big difference in terms of cost. So I expect to see more striking differences as I move to larger instances. So this was just an example of a simple partitioning mechanism that we could do using MILP information instead of, say, LP information. But there are a lot of next steps. This is ongoing work. So, of course, I should be implementing more stochastic events in the simulator. For now, I only have the arc delays as I showed you, but there are many other stochastic events that should happen and that will bring nonlinearity in the estimation of the objective function. I should be testing more advanced partitioning strategies. Very important to test on larger instances. Otherwise, as we've seen, we cannot really see the benefit of using one or the other. Of course, a sensitivity analysis on the DSO parameters. This does not only include the number of iterations, but could include also the sampling strategy, so how much attention I put to the partitions or not. And at the very end, of course, the MIP that I'm using now is actually quite different from the DSO in the sense that the mixed integer program includes a lot of constraints that are not present in the simulator, which means that there is quite a gap between what the MIP gives me as a solution and what the simulator would like to have as a solution. So another option could be to relax these constraints in the MIP, to solve the MIP with relaxed constraints, which means that it's a MIP that is closer, say I relaxed the Windows constraints, so it's closer to the simulation-based approach. But then there's no free lunch, right? There are pros and cons. What would happen is that the MIP would take much longer to to converge. The MILP would take probably much longer to provide me even with feasible solutions. But then maybe there is something to gain with respect to the partitioning and so to the DSO approach. So this is something that we will explore. So I take this occasion to tell you that I also worked on other directions in data-driven optimization, namely the integration of machine learning approaches within optimization. And this will be also covered in our next talk on October 24. So you're most welcome to join. And so thank you very much for your attention. I will be happy to take any questions if you have.